a great pleasure to be here and to deliver a talk on that great occasion at a conference held in honor of Professor Federico Sabina. Today I'm going to talk about structured bypass systems, and I call them smart bypass systems because we can control them, and certain types of so-called structured interface. And this is all related to waves, so we are talking about dynamic solids. Now, first I would like to give some background references, and of course the work of Professor Sabina on homogenization and wave propagation in homogeneous solids, in composites. This work has received a lot of attention in the research community working on modeling of waves, and these are some of the papers written by Professor Sabina and his courses, which are highly cited, and of course the work of Professor Sabina and Professor John Willis on homogenization and self-consistent analysis of wave propagation in composites, and then wave propagation in random composites and homogenization of magnetoelectroelastic materials, structured materials. And some additional references. Recently, there was an explosion of publications related to cloaking, and one of fundamental papers, highly cited, is the paper written by Milton, Brain, and Willis on cloaking for elasticity and physical equations with a transformation invariant form. For scalar problems related to the Helmholtz equation, cloaking was addressed much earlier in the framework of so-called geometrical optics, but elasticity is very different. And so this paper presents the concept of cloaking in elasticity in a very systematic form. Now, elastic structured materials are very interesting in the sense that you can take a structure that is nice and isotropic if you homogenize it in the static regime. For example, you can take a triangular elastic lattice, and as you homogenize it, it will give you nice isotropic medium. But try to look at such a lattice in the dynamic regime, and you will see that waves in this lattice will be dispersive, and at certain frequencies you will see strong anisotropy. And this strong anisotropy and ability to control waves by changing properties of lattices is a very attractive feature. So this are several papers, recent papers, related to dispersion and localization of elastic waves in materials with microstructure, and cloaking for flexural waves. And in particular, in these papers regarding cloaking for flexural waves, the discussion is about approximation of a cloak, because in some cases it's impossible to construct exact elastodynamic cloak, but you can construct a pretty good approximation. And of course, engineers, if they have some task at hand, they would like to make things as simple as possible and as efficient as possible. So what is the threshold? How much can you sacrifice by stepping aside from exact theory to an approximation in order to achieve the result? So we're going to discuss this. Now, First, let me talk a little bit about electromagnetic coupling and piezoelectric composites. And I'll start with a simple formulation that you would see in a stratified medium, where the axis of symmetry of piezoelectric material are chosen so that you can implement antiplane shear. So in this case, we are looking at EZ and UX components, and the wave propagates in the Y direction, and Z direction is the direction, ZX direction is the plane of the boundaries of layers. In this case, you can write two equations. Of course, there is a coupling, and then if you look for so-called Bloch waves, which are the waves that satisfy this relation, then you can see that for the amplitudes U and M, you can write this very simple system of equations. And it's a homogeneous system, and of course, you would like to have non-trivial solution, and the solvability condition for this system gives you the dispersion equation. So you can see that, yes, indeed, there is dispersion, there is coupling between electric and elastic waves, but if you take the numerical value for this coefficient, you can see that it's very, very small. So in practical terms, piezoelectric effect in many applications is a quasi-static effect, and you can see it very clearly from that equation. Formally, you can observe the coupling. In practice, this coefficient is extremely small. Now, but nevertheless, people do observe interesting features, interesting dynamic effects. So what are they, and where would you look at? The answer to this is interface boundaries if you have multi-phase structures. So, in this case, if you choose a two-dimensional structure now, and this will be a square, doubly periodic composite, and here you see elementary cell, and what you will do is you have two types of materials, and then you can either introduce thin interface, which may have just different properties, like very different stiffness, or you can play with the polarization. And piezoelectric materials allow you to do it. So in principle, you can have identical material in terms of elastic properties, but different polarization inside and outside, and this will create an effect. So then again, we choose the symmetry of the structure. In this case, the test computation was done for PZT5 ceramics, and that's the problem we looked at a number of years ago together with Professor Sabina. And then you can certainly see interesting dispersion relations and localization near the interface boundaries. So here, the electric potential is shown by color, so that's the surface. Then the actual electric field is shown by arrows, and the deformation is the deformation. So you can clearly see the localization near the interface. And then you can go further and look at checkerboard. And checkerboard, of course, is a very nice, simple object. And if you play chess, then you've seen checkerboard many times. But imagine that this checkerboard occupies the whole plane. So it's a periodic structure. Okay? And that's your elementary cell. And here in this simulation, we have PZT4 and PA66 used for plane strain computation. And in this case, as you choose the boundary of the Brillouin zone and just walk around, construct the dispersion diagram, then of course you would see absolute band gap, and it's not surprising. This would happen even without piezoelectricity. But if your polarization is the same on both sides of the interface, there isn't much change that you observe for this frequency range. But as soon as you change the polarization of the gray materials so that it's different from the direction of polarization of the white material, then you have a difference. So here you have solid lines, then you have dotted lines, which are hardly visible because they nearly coincide with the solid lines and dashed dotted lines that occur when you change the polarization. So this interfacial effect gives you quite a lot in terms of control of this kind of structures, and it's a genuine dynamic effect. One interesting feature that people probably don't talk about very much is the feature related to dispersion surfaces. So what does it mean? If I have a two-dimensional structure, then instead of plotting my dispersion diagram along the boundary of the Brillouin zone, I can take the function omega of kx and ky. Here they are normalized. And then plot a surface. Well, really, I need a family of surfaces. Here, I have a surface plot without piezoelectric effect. Here, I do have surface plot with the piezoelectric. Of course, the slope of the cones at the origin is higher. That's not surprising because you do have piezoelectric stiffening. But in addition, you can see quite substantial change in the higher order dispersion curves. And one interesting thing is, as you can see, there are some conical points on the dispersion surfaces. These are known as the Dirac cones. And Dirac cones give you locally neutral medium if you talk about transmission problems. And really, position of the Dirac point tells you about the angle of incidence and the frequency of the incident wave if you have a stack of checkerboard-like material, if you want to see pretty much undisturbed propagation through this. Now, the other feature of this is the so-called negative refraction. And this is something that you may expect if you see a checkerboard, just because it's a checkerboard. So imagine you have a slab of some structured interface, and you install mirrors inside. And these mirrors are half-transparent mirrors. So if you shine a ray of light, then this ray will reflect, but it will reflect in the direction that you wouldn't expect otherwise without the mirrors. So it's related to the so-called negative refraction. Now, if I plot the isofrequency contours, also known as the slowness contours, then I can see this negative refraction, and this is indicated by the non-convex shape of these contours. So in a way, if I take a wave vector, okay, from the origin to that boundary, then you can see that the normal to that boundary will be in the direction which corresponds to a negative angle. And the normal is the vector which shows you the group velocity, the direction of the group velocity. So that's a very sort of brief outline, but I hope I have conveyed the message that the interfacial effects in structures like piezoelectric checkerboards are very, very exciting. So now, as we know, we can have materials, microstructured materials, with properties which are unusual. I mentioned one, negative refraction. Well, this is a picture of a material with a negative Poisson's ratio. In fact, it used to be a movie. I wanted to run it, but since we had a problem with the connection, I had to convert it into PDF file. You can trust me that it's a negative Poisson's ratio material. So as you pull it, or let's put it this way, you roll it first, then you pull it, and instead of shrinking in the middle, it will expand. And it's a static problem. Now, this is another example of a microstructured material that has negative thermal expansion coefficient. Okay, and each ligament consists of two strips glued together, so it's a bimaterial strip, and then you interchange the material as you go over each junction, and when you heat it up, instead of expanding, it will shrink. Now, John Pendry, physicist from Imperial College London, introduced the notion of metamaterials. And that's his view on it. He says conventional materials are those whose properties can be derived from their constituent atoms. Metamaterials have properties that are derived from their constituent units. So these are microstructured materials, and these units can be engineered as we please. And the purpose, of course, is to achieve the properties that we want. Negative refraction, filtering, polarization, you name it. Now, the metamaterials I'm going to talk about are dynamic metamaterials, so we do have waves. And the first thing I would like to mention are so-called structural colors. If you travel to Australia and use Australian dollars, have a look at the banknotes. They're plastic. And these plastic banknotes have diffraction gratings built in. So when you look at it, you can see color. This color is not a chemical color, it's a structural color. Well, okay, so you can say Australian dollars are manufactured. These are man-made structures. Well, this is the example of a structure which is made by nature. It's so-called sea mouse. It's a little creature, little fairy creature, like a worm, and it lives at the bottom of the ocean, and it has very interesting hair. The cross-section of this hair has a pretty nice honeycomb structure, and if you run Bloch wave analysis on this kind of structure, you can construct a dispersion diagram, and you can identify so-called stop bands, and this will correspond to frequencies which correspond to the red light, and that's the frequencies you see. So this color doesn't fade. It will stay for as long as this structure survives. And it's a material made by nature. Now, let me give you another example. Suppose I take a triangular lattice, and in this triangular lattice, all links are the same elastic links everywhere. And then what I will do, I will take a strip, and inside the strip, I will redistribute the mass. I'm not going to change the mass density. So within the elementary cell, I maintain the overall mass, but I will bite off one particle and give a little bit to another particle, to the nearest neighbor. So gray and white particles have different mass, but their average is the same as the mass of the black particle. So overall, I haven't done very much. I didn't add any material. I haven't changed any elastic properties. And if you do standard static homogenization, this lattice will give you homogeneous isotropic material. It's just nice. Now, as soon as I start playing with waves, I identify immediately some effects. So this is the example when a point source was placed close to this interface at a frequency corresponding to the stop band for the biatomic structure which I have created. So there is a range of frequencies for which Bloch waves do not propagate through this structure. And of course, you can see it acts like a mirror, reflects everything. Then, for certain frequencies, you observe negative refraction. And therefore, if you place a point source, you can create a secondary source, the image, so-called flat lens, if you use terminology of John Pendry. Of course, there is reflection from the boundary, so you can say this signal is probably a bit faded, but still, you can see the secondary source. Now let me talk about cloaking. Now, first, I don't really think that cloaking is the best word to use. You can talk about the bypass system. And suppose you would like something simple, and you don't want to have any complicated theories. Common sense is a very good criterion, and very often you use common sense, and you can guess what the solution is, and then you can refine it. If you visited Sweden, then probably you've noticed that they use Scandinavian triple glazing. Now, double glazing, okay, but why would you need triple glazing? Well, the idea is very simple. Suppose you would like to isolate thermally one region from another. Then you have highly conducting layer, then a layer with very low conductivity, and another highly conducting layer. Looks okay? Maybe not. Imagine you have a hot spot or very cold spot, and then in the region of this hot or very cold spot, the heat will penetrate. And then, here we go, we have a problem. On the other hand, if inside you have additional one or several highly conducting layers, they can remove these effects of hot spot and redistribute the temperature uniformly. It's just common sense, but people use it, and they used it for many, many years. Here we go. That's a formal model. It's related to so-called transformation cloaking. Suppose I take Helmholtz equation and I apply a map, and this map is an invertible map. Then after the transformation, my new equation has this form, where C is now a matrix, and F here is the Jacobi matrix of the transformation. J, the determinant of F, is of course non-zero. Now, in this case, you can interpret this equation as the equation of a vibrating medium, which is inhomogeneous and has variable density. And it's perfectly nice, so it works. Then, we have, my colleagues and I in Liverpool, we have quite good interaction with engineering colleagues in Italy at Trento University. And they were very keen in building cloak. And we thought, okay, let's make something that is reasonable. So we wanted to propose a design which is reasonable. What is the best design? A lattice. Possibly a square lattice or something close to a square lattice. And of course, we don't want to use plane strain. We would like to look at a plate or a membrane. So let's start with the membrane. And we will look at square push-out transformation. And in this case, we'll start with the Helmholtz equation, and then we will distort the space by changing coordinates. Please note, I'm not talking about conformal maps. I make my transformation in such a way that the small, tiny hole now becomes a large hole, and the exterior boundary remains untouched. So that's what we do. This is done individually for all trapezoidal regions, and then they are glued here, near the corners. And it's pretty much explicit. So that's the formula for the transformation. that's for the first trapezoid, where the coefficients are given explicitly. Here, 2 epsilon is the size of the hole. Okay. And then what you have is you have a coating. And this coating gives you some kind of distorted metric if you think about propagation of ray. That's how ray will propagate. That's how it will propagate through this coating. The interesting thing is it's distorted inside, but outside it looks straight, like there would be no hole. When I say this, I have to be careful, because originally I said that this hole is tiny. So it's not the case that we didn't have any hole at all. It's very small, and therefore the scattered field is very low. So that's the approximation. Now, so then we have constructed this push-out transformation. We have a new material. It's anisotropic, okay, inhomogeneous, and it has variable density. And the matrix C is, and that's the new. It's the case of a membrane, okay, or you can think of antiplane shear, but it's better to think of membrane. So that's the idea. That's the object, and you send the wave around this object. And that's the result. As you can see, no obstacle, and that's the cloak. Perfect. Doesn't matter where your source is, still the result is pretty reasonable. The shadow has been removed. Now, next, I'm going to talk you through Kirchhoff plates. But since the time is running forward very quickly, I simply want to mention that it's not that easy, because the equations change, and you can't say that by doing this non-degenerate transformation you get equation of a plate. No. So what do you get? I'll give you the equation first. This is some extra terms that have to be interpreted, and it has been done, and what you get is a pre-stressed plate. So this is okay, and after that we can try to construct approximation of a cloak in an elastic plate. Let me go through. That's lattice implementation. And if you have a square lattice around it, it can mold very nicely inside. Now, it's been built, tested, and it works. Works like magic. So these are the computations. Uncloaked void, cloaked void. As you can see, it works pretty well. Now, this is so-called double slit experiment due to Young. It's very sensitive to the influence from the defect. And as you can see, C, cloaked object, the curve for case C practically coincides with the wave passing through 2 slits without any obstacle. So that's the implementation, and it gives you principal directions along which you can have your flexural stiffnesses being evaluated. And of course, there is a common sense approximation where you can just have rectangular lattice with a fairly high stiffness in the tangential direction and reasonably low stiffness in the transverse direction, similar to Scandinavian triple glazing. And believe it or not, it works. And that's the calculation for you. First, uncloaked void, you can see quite a bit of shadow. Then you have this very basic lattice cloak where you choose constant stiffness. You can see that the profile of the wavefront has been recovered. Now it's a nice profile. And then you introduce variable stiffness. The tangential ligaments become stiffer and stiffer as you approach the interior boundary, and for the transverse, it's the other way around. They become weaker and weaker. And in this case, it's nearly perfect. And I guess that's the time, so I'll better stop now, and thanks very much for your attention.
Thank you very much. There's time for one quick question. One quick question. When you are modeling the dynamics of interface, is there some sort of nucleation process in the model or some sort of origin of the dynamics at some point?
That's a good question. In this case, in all cases I spoke about, I assume that we have time harmonic problem. So I do not have a transient regime which requires setting the initial conditions. On all instances, we are talking about time harmonic regime.
Let's thank the speaker again.
Thank you.